Hello, this is Jehan and I'm here today to talk about caffeine, which is a personal favorite and important molecule to me. As a first-year engineering student, I'm bound to have a substantial amount of work and assessments to do. This is where caffeine plays a significant role in my university life. Without caffeine, I would not have the extra energy boost it provides to complete all these tasks efficiently on time, as caffeine's effect enables me to work with greater productivity. So what exactly is caffeine? Caffeine is a xanthine alkaloid compound that acts as a central nervous system stimulant to humans, having the effect of temporarily revitalizing mental alertness and preventing sleepiness. It can be found in varying quantities in the seeds, fruits, and leaves of over 60 different plants. In its pure form, caffeine is a very bitter-tasting white crystalline powder. As the world's most consumed legal psychoactive drug and the second most popular ingredient to be enjoyed in a beverage after water, caffeine is most commonly ingested in the form of coffee, as the primary and most popular source of caffeine, followed by tea, soft drinks, and energy drinks. On a scientific note, the caffeine molecule has the chemical formula C8H10N4O2. In this 3D model of a caffeine molecule that I have created, the black ball represents the carbon atoms, the white ball represents the hydrogen atoms, the blue ball represents the nitrogen atoms, and the red ball represents the oxygen atoms. As seen in the model, its molecular structure consists of two carbonyls, which are double bonds between oxygen and carbon atoms, one double bond between carbon and nitrogen atoms, one double bond between two carbon atoms, as well as two connected rings of nitrogen and carbon atoms with oxygen atoms connected to each one. In terms of how the structure of caffeine molecules facilitates their function as stimulants, caffeine's primary form of action is functioning as an antagonist of adenosine receptors in the brain. In Stephen Braun's book, Buzz, The Science and Law of Alcohol and Caffeine, he explains that the brain resembles a car with several brake pedals and several accelerators. Interfere with any one of these pedals and you will affect the speed and action of the car. One of the brake pedals Braun refers to comes in the form of the molecule adenosine, which plays a key role in simulating sleep and mental arousal. Adenosine is the byproduct of any working cell that can be found in most parts of the body. The harder a cell works, the more adenosine is produced, where it acts to gradually tranquilize the brain after a period of activity. Caffeine enters the scope in that its molecular structure is almost identical to adenosine's. Caffeine molecules are slightly smaller than that of adenosine molecules, allowing it to bind with greater ease than adenosine when it creates contact with the adenosine receptors on the neurons. However, caffeine molecules fit tightly but not perfectly in the adenosine receptors, which is why it does not initiate the same chain reaction in the cell as adenosine does. Instead, caffeine simply fills the space so that adenosine is unable to do its job of tranquilizing the brain, causing nerve cells to speed up, resulting in an increased neuron firing effect in the brain. In doing so, the pituitary gland that senses these activities naturally assumes that the body is under danger or stress, thus producing epinephrine hormones, otherwise known as adrenaline. This explains why after consuming a large cup of coffee, our heart rate increases, our muscle growth tense, and we feel a surge of energy and excitement as a result of the adrenaline hormones. There you have it, a quick understanding about caffeine.